chapter 15 today. Gonna finish it. We talked about this briefly yesterday, but I didn't do any examples, and I thought it'd be important to actually do an example since I just mentioned it in passing. So we said yesterday we had the general multiplication rule, where you took the conditional probability equation, you rewrote it, and you got this pretty equation right here. And that way you could multiply probabilities even if they weren't independent. I'll give you an example, so you might want to know in what scenarios you might want to use this. So here's a perfect example. 70% of kids who visit a doctor have a fever, and 30% of kids with a fever have sore throats. What's the probability that a kid who goes to the doctor has a fever and a sore throat? So you can just multiply the probabilities. Like having the probability of a fever and a sore throat, I'm just going to abbreviate, is the same as the probability of a fever times the probability of a sore throat given you have a fever. Well, the probability of having a fever, and the question was 0.7. This is like from the given equation. We just rewrote it. Right. Yesterday, let me finish this question, I'll go back and show you the equation yesterday. What's the probability of having a sore throat given you have a fever? 0.3, that's what this says, right? A kid's with a fever that has a throat. So that's sore throat given you have a fever. So this probability is 0.21. So yesterday's equation said the probability of B given A equals the probability of both divided by the probability of what was given, right? So we just multiplied it to undo that. We want to know the probability of getting both. And I know this and this, but I don't want to know this. So I just multiply. So you have all the pieces, it's just rewritten. Does that make sense? So you could still use that formula, it's on the formula sheet, you could fill it out and then realize, oh, I can just do some algebra and get that answer anyway. Okay? Questions about that? All right. Then we're going to finish the rest of chapter 15. Again, I'm going to be skipping around a lot today. It's going to seem like I'm doing a bunch of random things. So we're just going to talk about a bunch of different stuff that can happen using probability. Okay? First thing, really easy. Drawing without replacement. Perfect example is cards. So remember in chapter 14 we were talking about independent events. So like 3 people walked into the shopping center and rolled the discount die or whatever. Or you picked 3 M&Ms in a row from a big, huge factory full of M&Ms. Right? So it was independent. They didn't influence each other at all. And so you just did the probabilities of their power, no big deal. In this case, with cards and other events, the card is the easiest. If I'm passing you a hand of 3 cards, right, pulling out the left the other, you're reducing the sample that's available to you, which means you're reducing the probabilities that are available to you. Because I've done these before. I'm going to remind you of all these things that are happening. So I won't do all of these, I'll do like 2 of these, just to make sure we're on the same page. Alright, so you are dealt a hand of 3 cards, one at a time. Find the probability of each of the following. So let's do A and D. So A says, the first heart you get is the 3rd heart dealt. Well, that's the probability of not getting a heart, and then not getting a heart, and then getting a heart. Right? So, just initially, first of all, how many hearts are there in the deck? 13. So how many cards are non-hearts? 39.
So the first card you get that's not going to be a heart, there's 39 out of 52 cards that aren't a heart. Agreed? But now you're keeping that card. So the next card you get, there's only 38 cards that aren't hearts left. And there's only 51 cards total. And then the next card you're going to need is a heart. How many cards are left? 50 cards.
And so then you would multiply the fraction straight across. That ends it. You're trying to get a heart the last time. Does everyone understand part A? Again, you guys have seen without replacement before.
But I'm going to do part D because I want to make sure I can actually do this.
On part D, find the probability that you have at least one ace. So if you're doing the probability you get at least one ace, what does that mean? How do we do that? Right. So 1 minus the probability of no aces. And again, you're doing 3 cards in a row, right? So this time you can't do something to the third power because it's not all the same probability. So, how many cards are aces? So how many cards are not aces? So the first card you get, if you're trying to get no aces, you have 48 out of 52. But the next one you have, and then the last one, you would need to multiply all of those together and then subtract from 1, which should end up being 0.217. Can you all handle without replacement? Just keep those things in mind. In chapters after Christmas, when we're talking about probabilities, don't be like a spoon of a probability type situation as this. But we'll be talking about how the sample size is big enough that it doesn't matter because you're not taking the probability that it doesn't matter. But for now, you have this finite number of items, cards, cats, whatever you're talking about. If you take one, you have to reduce the amount you have for the next one. Does that make sense? Okay, excellent. Next topic. I'm just getting around all the place today. We talked about conditional probabilities yesterday. We talked about contingency tables yesterday. You know how to make a Venn diagram, but sometimes the problem is complicated enough that maybe you don't want a Venn diagram, you like a table. You can't always find conditional probabilities from a Venn diagram because there's so much stuff going on, it's more potential to mess it up. So here's an example where you can make your own table. So they have this drunk driving example going on in the book. And it says that we're told that 78% of suspect drivers get a breath test, 36% get a blood test, and 22% get both. That's enough information so that you can make a table of probabilities. So this is from your book, so it's already halfway done. But the two options are blood test or breath test, right? They have yes and no. So the people that got both is the 22%. 78% of all of them got a breath test, that's total. And 36% got a blood test, that's total. We know the probability should add up to 1. So we could go back in and fill all of the other boxes in with that much information. Okay? This one's in the book, so I'm going to do a different one. We'll have to do it on our own. Okay? But do you understand the concept? You have all this stuff going on. You can vary using a Venn diagram of that. I think with the next question, it's a little more complicated, and I think the Venn diagram will be confusing. So it would be easier to have a table. That's just my opinion. To finish this table, you would do like 0.36 minus 0.22 to get that no section. And you would do 0.78 minus 0.22 to get that no section. And then for this section, you would do 1 minus 0.78. This would be 1 minus 0.36.
95 adults, 81.5% of who were over 30. The National Sleep Foundation reported that 36.8% of all the adults snored. 32% of the respondents were snorers over the age of 30. What percent of the respondents were under 30 and did not snore? This is a nice little table. So what is one of our categories? What about middles? Over 30, so then the other ones have to be under 30. And then what's the other category? Snorer, no snorer. Right? What are all the probabilities going to add up to be in this table? One. So this little corner right here we know is only one. Right? It has to be. The probability have to add up to one. Table.
Has to one.
Alright, so let's look what we've got. 8.5 and a 4. So we're right. 36. 36.8% of Ronald snore. And then 32% of the respondents were snorers over the age of 30. Like, I can fill everything else in. Alright, let's start with the snore column. How am I going to find the under 30 snorer? 0.368 minus 0.32, it should be 0.048. And do the row and column totals. So what's going to be the very bottom row total? How are you going to find that? Right, 1 minus 0.368 is 0.632. And then what about the total on the right? 1 minus 0.815. And then so what's the under 30 no snorers? And the over 30 no snorers. Right now, a very pretty table. I'm going to use the answer questions. Okay, so 1A, what percent of the respondents were under 30 and did not snore? 13.7% of the asked snoring percentage. But that was one of the last ones that we thought would back up, right? So, I'm going to take a look and then we don't have to take a look at this actual picture. On B for the snoring independent of age playing. Now, we can probably make it conjunction. Do you think snoring is independent of age? But there's got to be a mathematical way to decide that, right? So, those are the formulas. So far we've talked about pretty much 4 formulas, right? With a general addition rule on your AP stats formula sheet. Yes. The conditional probability formula on the AP stats formula sheet. The multiplication rule that we talked about earlier today is just the conditional and rewritten, right? So this one is the only one that's really not provided to you. Right? So it says for events to be independent, that for the probability of B given A, that has to equal probability of B if they're independent. If they are equal to each other, then those events do not influence each other. If they are not equal to each other, then those events do influence each other, so they are not independent.
can pick whatever is given that you want, but
I'm going to stick with what was the original question. I know that's sound, and I didn't make any mistakes or nothing. So what conditional probability is given to me in that question? Which one of those percentages is conditional? Or which one is going to help you find a conditional one?
right. So we have the probability that I'm probably writing it the correct way. Age given they snore. Snore given age. They were snore. It doesn't really matter. We can do whatever we want. Yeah, it doesn't really matter. So which one do you want to do? Tell me which one you want to do. Snore given age equals, it has to, we're going to find out if it does. Probability of snoring. We don't know. That's why there's a question mark. I'm not sure. Okay, so we got to use the formula for given probabilities. This is the probability of snoring, and we got to pick an age, over 30 or under 30? Over. And over 30 divided by over 30. Right, that's the formula from yesterday. If you're trying to follow this formula, then you have to have something given something else. And even though 32% is an intersection of two, it's just an intersection. It's not like conditional. It's just both. All right, so using our table, what probability are snorers and over 30?
That's the 0.32, right? And then what probability are those over 30? 0.815. And then the probability that people snore is what? Right, that's all from my table. They're on zero people. You could have picked any order or anything you wanted to do up here. You could have done probability of not snoring, given there, under 30, whatever you wanted to do. You still had to follow the formula. Okay? So what's 0.32 divided by 0.815? So that's nice and close and all. But it's not equal. So that shows that they are not independent events.
They have to be equal. Yes.
I did 0.32 divided by 0.185.
Again, this
would have worked if you used any two you wanted to. So you give them the probability of under 30 given they snore. You just follow the same formula. You get whatever. And we have this table, so you have all these probabilities you could use. Whatever one you want. Doesn't matter. Questions about that one? We'll do another one with independence in a second. They have to be equal or independent. Right, so here, instead of really explaining, if you show all of this, then you've proven that they're not independent. You have to be very, very persuasive and use statistical language. Only sufficient to say older people snore, so they're independent. Even though that is intuitive. So, later on, it won't, not that it won't matter much, that you'll have to know it. Alright, questions on this one? Alright, what am I at? Alright, got 3 more slides. Here's another independence question. So in the real estate ads described in exercise 1, 64% of homes for sale have garages, 21% have swimming pools, 17% have pool features. So I'm like, hey, if a home for sale has a garage, what's the probability that it has a pool too? What does that mean? We'll find it. The probability of a pool given a garage. Over the probability of right, so what's the probability of both? The 117 question was part of the garage. Are having a garage and a pool independent events. So this one's less intuitive, like I don't know, probably independent. It's not like the last much for older people tend to store more, right? We know that disjoint, but that doesn't mean they're independent. So we gotta use that independence bit. So it says probability of B given A equals the probability of B if they're independent. We already have a conditional probability. We've already computed it, correct? So why don't I just use that one? Do you have to use that one? No, but I've already done it. So I'm just going to use part A as my piece that's given to me, my conditional. You don't have to do a whole new one if you want to, but I've already done it. This would have to equal the probability of having a pool. So they're not equal. This one's 0.266, and the probability of having a pool was 0.21. So they're not equal, so they're not independent. Part C are having a garage and a pool mutually exclusive. What does mutually exclusive mean? Disjoint. So are these disjoint? Can you just overlap? Yes, so they're not disjoint, right? They can pool in the garage at the same time. If there was no overlap, they'd be disjoint. Not disjoint. So no, when we can explain something about an overlap, or you can have a pool and a garage at the same time, or something. Disjoint events have nothing in common.
Questions on this one? All right.
2 more. Tree diagrams. I like tree diagrams.
And I am not awesome at the probability. So if I can draw a picture, I'm in a much better space and I'm much better off than where I would have been if I was trying to figure it out. So maybe some of you guys are way better at probability than I am, and you can just figure things out. I need a formula or I need a picture because that makes me think it through and know that I'm doing the right thing instead of just trying to put numbers together in my head. In a tree diagram,
Says of events. Something happens or something else happens, and if this happens, and if this happens, this doesn't happen, those types of things. Where it's like these branches of possibilities. So I've got 2 questions you can choose from. You can choose from the luggage question or the dishwasher's question. Dishwashers or luggage. probability her first flight leaves on time is 0.15. If the flight is on time, the probability that her luggage will make the connecting flight to Chicago is 0.95. But if the first flight is delayed, the probability that the luggage will make it is only 0.65. So you can see in this perfect example there in a sequence of events that is about to happen, right? The flight is on time and her luggage makes it, or it's on time and it doesn't make it. Her flight is delayed, but her luggage gets there in time, or her flight is delayed and it doesn't get there. Right? There's all these different possibilities. So as I'm trying to figure out the answer to these questions, I'm going to tree diagram first to make sure I have all of the possibilities all nice right now. Right? So that's where it is a tree diagram. So her name's Leah. So we got Leah going this way. You have two options. Her flight is on time, or her flight. What's the probability that her flight initially is on time? Which means the part that's delayed is what? Because they don't tell us that one, but we should be able to figure that out, right? Those two have to add up to be 1. Agreed? Okay. Then there was an extra set of conditions, right? If the flight is on time, the probability that her luggage will make the connecting flight to Chicago is 0.95. So luggage makes it. Or that means her luggage could also not make it. So what was the probability that it was going to make it? Okay. So what's the probability that it doesn't make it? So these two have to add together to be 1. Right, but the same scenarios are available for if the flight is delayed. So her flight could be delayed and the luggage could still make it. Or the luggage doesn't make it. I don't know. It said in the question that if the first flight is delayed, the probability that the luggage will make it is only 0.65. So if it's delayed, the luggage doesn't make it, what percent of the time? Again, those two have to add together to be 1, right? Well, now we have these conditional probabilities that we can use these multiplication rules. Right? So this part up here would be the part that's given, typically. But I can find all of these probabilities. So if I can find the probability the luggage makes it even if she's on time, I can do that by multiplying that across these numbers. So that would be 1 or 2. I can find the probability the luggage doesn't make it even if it's on time. If I multiply back across the 1 and 5, and 1 and 5. And so on and so forth. Yeah. So all of these together have to equal 1 as well. So at every little stage of the game, you start looking at the probabilities. Now I have 1 point to make before I finish the question. These tree diagrams do not work backwards. So if I'm given this information to make a tree diagram, I can find these probabilities at the end. So I find the probability the luggage makes it even if it's on time. I can flip-flop that and still work. I can find the probability that it's on time given the luggage makes it. Doesn't work. We need to have a completely different diagram for that, where the luggage was the first event that was happening. Okay? We can talk about that on Monday. Alright, so let's answer these questions.
Alright, you can do it. It's 2 questions.
Part B. What is the probability that her luggage arrives in Denver with her? Her luggage arrives in Denver, so 0.1425 is part of it. Her luggage also arrives with her. It's delayed. So then you add those together. planning on